All the launches from the tower that we have discussed so far were made at some positive angle with the horizontal. Now we will discuss an interesting case, that is, when a projectile is launched horizontally from a tower, so it is launched parallel to the ground. Another way of putting this is, the projectile is launched with theta as 0, and we want to find the time of flight of this projectile. The concept that we need to apply is that since the initial velocity imparted to the projectile is completely along the x direction as it is launched horizontally, the initial velocity component along the y direction would be 0. The entire initial velocity is along the x direction. This is the important part to understand in this special case. Having understood this part, all we have to do now is to apply the equations of motion independently along each axis. Let's apply the second equation of motion along the y-axis. So we have y minus y0 equals v0y times t plus half at squared. Now we try plugging in the values that we have. Our reference line is the horizontal line passing through the launch point A. The initial y displacement y0 is 0 since at that point in time the projectile is on the reference line. The final y displacement is minus h, where h is the height of the tower, and minus h since it lies below the reference line. As discussed, the initial y velocity component v0y is 0 since the initial launch velocity is completely in the x direction. You can think of the initial component of the y velocity as v0 sine theta, and since theta in this case is 0, v0 sine theta would also be 0. The acceleration is minus g since it is in the downward direction. So we solve for the time, and this turns out to be the square root of 2h over g. Do you notice anything special about this time which we have derived as the square root of 2h over g? One interesting thing about it is independent of the horizontal launch velocity, v0. So if we threw a ball horizontally from the top of a tower of height h with a speed of, let's say, 10 meters per second or 20 meters per second or 100 meters per second, it would take the same amount of time to land on the ground, which is the square root of 2h over g. This is very interesting. How much time would it take if instead of throwing it horizontally with some speed, we just release it from a height of h? Which in technical terms would mean that the horizontal component of the initial velocity is 0 in addition to the vertical component of the initial velocity being 0. According to this formula, the time would be the same. It would continue to be the square root of 2h over g for a ball dropped from a height of h to reach the ground. To prove this, let's compare the downward movement with one ball just released from rest and the other ball thrown with a certain horizontal velocity. The green ball is released from rest and the yellow ball is thrown with a certain horizontal velocity, v0. We take a snapshot at a certain moment in time and we find that the y displacement of the green and yellow balls is identical as shown by the horizontal dotted line joining them. Let's watch a few more frames. And you can see that their y displacements are always identical. Both the balls eventually land together. The green is simply released from the top of the tower and the yellow one is thrown with a horizontal velocity. The range of the green ball is 0 and the yellow one has gone some distance based on its velocity. And this happens because when we set up the second equation of motion along the y direction, the initial and final displacements in both cases are the same. Their initial velocities are the same, and g is also the same. So the time of flight also therefore happens to be the same. This is the comparison when the green ball is released and the yellow ball is imparted some small horizontal velocity, and you can see that they landed at the same time. Now what we will do is to impart a substantially greater horizontal velocity to the yellow ball. Let's see what would happen. Well, its range increases, but the time of flight remains the same for both balls. So both of them continue to fall together, the green released from rest and the yellow imparted a horizontal velocity. If we need to compute the range, then we fall back on the concept that the x component of velocity remains constant throughout the flight. The projectile is launched horizontally with a speed of v0 and it continues with the same x component of velocity throughout its flight, as there is no acceleration in the x direction. So everywhere along this trajectory, the x component of velocity remains 0 even as it lands. And since we are measuring the range in the horizontal direction, the range would be the constant x component of velocity times the time of flight. So the range would be v0 times the square root of 2h over g, since regardless of the velocity, the time of flight remains the square root of 2h over g. You can see here that the range is directly proportional to the initial speed. Can we apply the trajectory equations when the launch of the projectile is horizontal? Absolutely. The trajectory equations are valid for zero launch angles as well. If we substitute 0 for theta, we obtain y as minus gx squared over 2v0 squared, as tan of theta would be 0 and cos of theta would be 1 when theta is 0. And as you can see, y will always be negative here, since the y displacement will always be below the reference line. The cases we have just been through are cases where the projectile would have only an initial horizontal velocity, but no initial vertical velocity. Or in the case where the ball is released, so it neither has any initial horizontal velocity nor any initial vertical velocity. And in these cases, it doesn't really matter how much the initial velocity of the launch is. The time of flight remains the square root of 2h over g. But remember that this is possible only in cases where the initial vertical velocity of the projectile is 0. So the initial velocity should not have any y component. When a projectile is launched horizontally without any vertical component of initial velocity, the time taken by the projectile to land would be the square root of 2h over g, independent of the speed of launch.